5.3, common factors. We're going to work through these investigations really quickly, but just as a review, we want to know how algebra tiles work. So basically, when you're creating a product, so when you're multiplying two binomials together, or a monomial and a binomial, or whatever it is, you're going to end up with a product. When you multiply two factors, factor here, you end up with a product. And now what we're doing, instead of having our two factors and multiplying them to get our product, now we have our product and we want to split it into the two factors. One easy way to do that is to make a rectangle with what you have. So basically we have a binomial, 2x plus 4. That's represented here. 2 x's, 4 1's. And we're going to factor it. That means split it up into its factors. So we just need to look at it and say, okay, how long is the length, how long is this side of the rectangle that represents our product? Well, this bar has a length of x, so there's 1x, and we have a length of 1, 2, 1. So this is x plus 2. Over here, we have this length and this length. So if this bar is 1x, then it must be x times 1. Same with this bar, it's x times 1. So here we have 1 and 1, which is 2. So the factorization of 2x plus 4 is 2 times x plus 2. And if we think about it backwards, just to kind of double check our thinking, we can see if we have the group x plus 2, and we have that group 2 times, well, we'll have 2 x's, and we'll have 2 2's, which is 4. Looking over here, this time we have a different product. It's represented down here in its rectangle and made with algebra tiles, and we're going to split it up into its two factors. So we think about the length of the sides that we're working with. Here we have a length of x, and here we have a length of 1 and a length of 1. That's going to be x plus 2. And then here we have just the length of x. And if we think about it, multiplying it back into our rectangle, x times x is x squared. X times 2 is 2 x's. So what do we have? We have x squared plus 2x equals x times x plus 2. So in both of these cases, we have a monomial times a monomial times a binomial, and you can always double check it by in your head multiplying it back. X times x is x squared. X times 2 is 2x. Okay? Investigation B, using the greatest common factor to factor a polynomial. So our goal here is to find the greatest common factor of each set of numbers by first expressing each product as a product of prime factors. So all we're going to do here is we're going to take, and there's a couple different ways to do this. You can do a factor tree, in which case you would take the number 12 and split it into two factors. So what two numbers could I multiply together to get to 12?
6 and 2.
Sure, 6 and 2. I can't split 2 anymore. The only two factors of 2 is 1 and 2, but 6 I can split into its factors. What are they? 3 and 2. So for the number 12, 3 times 2 times 2 is its prime factorization. That means you've factored it as far as you possibly can into numbers that can't be factored by anything other than 1 and themselves. Okay? Let's do the same thing for 8. Give me two factors for 8. 4 and 2. 4 can be split up into 2 and 2. So the prime factorization of 8 is 2 times 2 times 2. Now, we can look at these and we can say, what is the greatest common factor? Well, the greatest common factor is the product of the factors that they have in common. What does that mean? Well, I look at the 12 and it has 3, 2, 2. I look at the 8, it has 2, 2, 2. So they both have two factors of 2. 2 factors of 2 is 4. So they both have a greatest common factor of 4. The factor tree is a really helpful way to break it down. If you get really good at this and you don't need a factor tree, then you can simply list the two numbers. So for instance, 15 I can look at and you split it up into 3 times 5. So its factors are 3 and 5. Well, both of those are prime numbers. They can't be split up any further. So that's as far as it goes. 25 is another pretty straightforward one. Its only factor is 5. It's 5 and 5. Okay. So I'm going to write that down, 5 and 5. And really, you could put the multiplication sign in there. That probably makes it easier to understand. Okay. And so what factor do they have in common? Well, they have one factor of 5. So greatest common factor between 15 and 25 is 5. Go ahead and try and list the prime factors of 6, 18, 24, and then think about what they have in common. Sorry to speed along, but hopefully you came up with this. You have the factors of 6 are 3 and 2. 18 is 3 times 2 times 3, right? It's 6 times 3. 24 is 8 times 3. So I've already organized it in a way that I can see that they have the factors 3 times 2 in common. So I can even kind of just circle those. That's what they all have. And tells me that the greatest common factor of 6, 18, and 24 is 6. Okay, that means 6 is a factor of 6, 6 is a factor of 18, 6 is a factor of 24. And if I wanted to factor out something from each of these terms, and the factoring out would include the greatest common factor, then I could express 6 as 6 times 1. I could express 18 as 6 times 3. I could express 24 as 6 times 4. That's what it means to factor out the greatest common factor, which is what we're going to be looking for in the next section. So this time we're finding the greatest common factor of 9 and 12. Then we're going to write each of those numbers as a product of only 2 factors, where the first factor is the greatest common factor. So what's this getting us used to doing? It's getting us used to, for instance, seeing something like this and pulling out the greatest common factor of both of these terms. Well, the greatest common factor of both of these terms is 2. So we pull out 2. It leaves us with x, because x times 2 is 2x. And it leaves us with 2, because 2 times 2 is 4. Okay? That's what we're working toward. So 9. If we can factor out 9, it's 3 times 3. That's its prime factorization. 12 is 3 times 2 times 2. Okay? Well, now we want to write each number as a product of only 2 factors. Number 9 is already done. It's only 2 factors, and both of the factors are 3. So that's pretty easy. But 12 has 3 factors in it. Now I want to write it as a product of only 2 factors, where the first factor is the greatest common factor. Well, what's the greatest common factor between 9 and 12? 3. It's right there. Okay? So when I rewrite 12, I'm actually going to rewrite it as 3 times, and my second factor has to include the rest of the information that's left over, which is 2 times 2, which is 4. Okay? So 9 is 3 times 3, where 3 is the greatest common factor, and what's left over is 3. 12 is 3 times 4, where the greatest common factor is 3, and the factor that's kind of left over to make 12 is 4. So that's how we're thinking. All right, because of the rules of exponents, we know how to do these next ones as well, but basically we'll write it for the first one and then we'll probably cruise through the rest. But what does 7 cubed mean? Yeah, it's 3 factors of 7. 7 times 7 times 7. 7 squared, 2 factors of 7. So if we know how to work with these, they actually become really easy. 7 squared is contained within 7 cubed. 7 times 7 is inside 7 times 7 times 7. So the greatest common factor here is 7 squared. if the base is the same, then the greatest common factor is just the term that has the fewest multiples of that base. So 7 times 7 fits right inside 7 cubed. Using that, let's just do it quickly. What's the greatest common factor of 5 to the power of 6 and 5 to the power of 4? 5 to the power of 4. There are 4 factors of 5 in this term and no more. And there are 4 factors of 5 in this term and 2 more. Okay? So the greatest common factor here is 5 to the power of 4. Well, what if we don't have numbers? What if we have variables? We have 3 factors of x and 2 factors of x. Well, 2 factors of x are common to both terms. And that's the greatest common factor. So the greatest common factor here, just like the other ones, is x squared. And you could express x cubed as x squared times x to get that third factor. Good. Number 4. Find the greatest common factor of x to the power of 6 and x to the power of 4. Then write each number as a product of 2 factors, where the first factor is the greatest common factor. So again, we know that the greatest common factor between these two is x to the power of 4. Okay? So let's rewrite each as a product of 2 factors, where the first factor is the greatest common factor. Well, if the greatest common factor is x to the power of 4, then I need to write x to the power of 4 as a product of 2 factors, one here and one here. Well, if I pull out all 4 factors of x from here, what's left? Don't say 0. 1. Okay? I have 1 times these factors. Remember, anything times 1, or 1 is a factor of every single number, because you're talking about multiplication. 1 is always a factor. This is going to be really important because you're going to need that. It's kind of like a placeholder. It's not really a placeholder, but you're going to be factoring out 1 from things every once in a while, even though it doesn't change anything. It's really helpful when you factor out -1, because it doesn't change the value, but it changes the sign. And sometimes you might have to see that 1 is the only factor left over once you factor out your common factor. All right, x to the power of 6. If we take out 4, if we divide out 4 factors of x, how many factors of x are left? 2 factors of x. X squared. Good. Now we're going back to a polynomial. It has 2 terms involving x. And right away I notice it actually has 2 terms involving a multiple of 2. So when we're talking about greatest common factors, I've got a feeling that it's going to involve the number 2, and it's going to involve the letter x. Find the greatest common factor by first expressing each term as a product of primes. Well, this works the same way as numbers, except now you have numbers and letters. What are our factors? We have a factor of 2, and it's connected by multiplication to 2 factors of x. So we have 2 times x times x. Following? Let's look at the term 4x. The term 4x has a numerical part, the coefficient 4, which can be factored into 2 times 2, and it has 1 factor of x still. So now we can see what is the greatest common factor. What factors do they have in common? Yeah, they both have at least 1 2, and they both have at least 1 x. So the common factor then is 2x. Now we're going to rewrite the polynomial, this polynomial, as the sum, pay attention, the sum of products where each term is the product of 2 factors. So we're going to rewrite it. We're going to have a term here, a sum, and a term here. And each of those terms is the product of 2 factors, where the first factor in each term is going to be the greatest common factor. Okay, so we're taking 2x squared, and we're going to rewrite it as the product of 2 factors, where the first factor is 2x. Well, what's left over in 2x squared once we've taken out 2x. You can see if you've done the prime factorization, we still have a factor of x left. Okay? It's a little bit confusing with this. This is a multiplication sign. We'll just change it to that so it's very clear, but now you have 2x times x. Okay? Well, what about our next term, 4x? Can we rewrite that as the product of two terms, two factors, where the first factor is 2x? We sure can. What's left over? A factor of 2. So we haven't changed the value of it at all. All we've done is expressed both terms as a product of two factors, and the first factor in each term happens to be the greatest common factor because we thought, well, what's the greatest common factor between these things? What this allows us to do is think of this now, these are just two terms. There's a term here and a term here. But now these two terms have something in common. They have 2x. 2x is in both of these terms. So what I can actually do is I can write 2x here. And then I can draw a little bracketed group. And I can see that 2x needs to be multiplied by x. And 2x needs to be multiplied by 2. And those things need to be added together. Added together. So if I have 2x times x, that's right there. And then I need to add that to 2x times 2, which looks like that. So in reality, when we get good at this, we can go straight from 2x squared plus 4x, and we can just pull out the greatest common factor of each term, and then say, okay, well, what factor is left over that needs to still be multiplied by my greatest common factor? In 2x squared, it's x, and in 4x, it's 2. And this is called the factors of this polynomial, okay? This is factoring. You've pulled out the greatest common factor, you've seen what's left over, and that's really what we're working on in this lesson and in this whole unit. Okay, something to think about before we get going into the notes on 5.3, but the goal of today, you already know that if you have a factor and a factor, you know how to multiply those together, right? That would look something like this, and you would FOIL them. First times first, outside times outside, inside times inside, last times last, and maybe it's a monomial times a trinomial, okay? Then you'd make sure this monomial gets distributed to all the terms within the trinomial. That's distribution. That's how we multiply. That's what this is. If you're given two factors, they come together, every term multiplied by the terms in the other factor, and that's going to get you the product, okay? Today, what we want to be able to do is we want to be able to start with this product. That's what this unit is about, and we want to be able to split it out into its factors. Okay, if those diagrams are helpful, copy them down. Another way to think about this, and it's on the very front of your book, but basically if you're going from, let's say, x squared plus 4x plus 4, and that's equal to x plus 2x plus 2. It's not a great example because it's a binomial squared, but at any rate, if you're going this direction, which you're used to, it's called expanding. And today, we're going to be going this direction, which is called factoring. If you don't know that, write that down really quickly. And then I'm just going to work down beyond that dolphin sentence to why might it be useful to be able to go from this expression to this expression. Okay? It can be useful. Rewriting the expression using common factors can help simplify the expression. So under that question, you can write to simplify the expression. And what's really key is to provide helpful information. For instance, you already know that this form reveals where the graph of a polynomial hits the x-axis. So that can be pretty helpful in real-world situations. Okay, so it's going to provide us helpful information for graphing and problem solving. For graphing and problem solving. Okay, we've done a couple of investigations. Now we're going to get into our examples and we're going to work through them, like I said, fairly quickly. Okay, in example 1, we're asked to use algebra tiles to factor the binomial x squared plus 3x. I haven't handed out physical algebra tiles, but x squared looks like this guy, and x's are bars of unknown length, length x. And so what we're going to do is we're going to just make a grid built by those algebra tiles. And when you're using algebra tiles, really all you need to make sure is that you've created a perfect rectangle. If you've created a perfect rectangle, then you can represent it as factors, which are its length and its width. Okay? So all we have to say here now is, well, what length of tiles do we have here? We have the length of x plus 2. Oh, sorry, I misdrew. We're supposed to have 3 x tiles. So go ahead and add a third x tile to your rectangle. X plus 3 now, and the length along here is x. Okay? So really simply, you can see visually with algebra tiles that x squared plus 3x equals x times x plus 3. And just so that we're reviewing our concepts, look at this term. We pulled out a factor of x. What was left? A factor of x, x squared. Look at this term, 3x. We pulled out an x. What was left? A factor of 3. Okay, that's really kind of how you can picture it. You're pulling out factors and then seeing what's left over, and that is the length and width of the rectangle that if you multiplied back together, you would get this expansion. Okay, excellent. In example 2, we're going to run through a whole bunch of quick examples. I'm going to work through them very quickly. Okay. Example 2a, we have 6x plus 3. There are 5 examples, by the way, that need to fit on that page, just so you know. That's how small you're writing. Okay? Well, greatest common factor between each of these terms? What is it? Greatest common factor between 6x and 3.
3.
There's a factor of 3 in both of those. Well, if I pull the factor of 3 out of our first term, I still would have to multiply 3 by 2x to get all of that same value. Now, here's what we need to think about. What factor is left behind if I divide 3 by 3?
1.
I need a factor of 1. If you don't write anything there, if you say, oh, that's 0, or oh, it's done, you've lied. You've said that 3 times 2x is the same as this. It clearly isn't. That would only get you 6x, and you would not have a product of 3 to add to that polynomial. So you need to make sure you have that factor of 1. Now, if you multiplied it back, you'd get 6x plus 3. All right, B. If you want to work down or across, do whatever works best for you. B is 8x squared minus 7x. This one's a little bit trickier. I look at my number part and my letter part. Is there a common factor between my two numerical values? 8 and 7? No. 8 can't be divided by 7 using whole numbers, so it doesn't work. But is there among the variable factors? Yeah, there's 2 factors of x here and 1 factor of x here. So I can pull out an x from both terms. My first term, that's going to leave me still with a factor of 8 and 1 factor of x, so 8x. And in my second term, I bring down my negative because I pulled out a positive x, and I need to have a negative term. So that factor that's left is going to be negative 7. Okay, I'm mentioning things that you can pay attention to as we move along as well. C. C is a bit bigger. 25 times k to the power of 6 plus 15 times k to the power of 4. So now you can really see you're pulling together all those things that we did in the investigation. Let's first look at the numerical part of our term, the coefficient. Do they have a common factor, 25 and 15?
5.
It's 5, and that's the greatest common factor, so I pull out a factor of 5. Can I pull out any factors from my variable? Yeah, I can pull out 4 factors of k and 4 factors of k. So my greatest common factor then becomes 5 times k to the power of 4, or 5k to the power of 4. And what's remaining in my first term? Well, the numerical part's easy, 5 times 5. And how many factors of k? Still have 2 factors of k, so k to the power of 2. Now on our next term, the numerical part is easy. I'm left with 3. And if I divide my variable part, 4k to the power of 4 divided by k to the power of 4, I'm left with a factor of 1. But look what happens. I don't actually need to write it in this case because I already have a value of 3, and that will get me 3 times this is 15k to the power of 4. Multiplying 3 by 1 doesn't change anything, just gives us 3, so I don't write that step. Good, carry on, D. D, we have 21 c to the power of 4 d to the power of 3 minus 28 c squared d to the power of 5 plus 7 c d cubed. Again, now we're going to be looking at kind of 3 pieces in each term. They all have a numerical part, they all have factors of c, and they all have factors of d. And we need to make sure we're pulling out our greatest common factor. So let's talk about numbers, 21, 28, and 7. 7. They're all divisible by 7. So let's pull out a 7. Factors of c, this one has 4 factors of c, 2 factors of c, 1 factor of c. So 1 factor of c is common to all of them. Factors of d, 3, 5, 3. So d cubed is part of our greatest common factor. And now we're going to go through. We're starting with a trinomial, so we're going to finish with a trinomial. 1, 2, 3 inside that bracket. Okay? Well, let's look at each term inside of the trinomial. 21 divided by 7, I'm still going to have a factor of 3 left over. I'm going to have 3 factors of c, and I'm going to have no factors of d. Just 1, right? 1 times d cubed is d cubed. So I don't need to write the 1 in this case because I already have a place value. I already have something to multiply against in order to maintain, in order to get back to this term. All right, let's look at our next term. 28 divided by 7 is 4. So I want to remember also that it's negative. This is a negative term, and I've pulled out a positive factor. So the factor remaining must be negative. Okay, so I have negative 4. Instead of c squared, I've pulled out one of those factors, so I still have a factor of c, and I still have 2 factors of d. Now our next one is tricky. I look at it, 7 is already accounted for, c is already accounted for, and the d cubed is already accounted for. What do? I have to, and it's positive, so I need to add 1 in order to stand as a multiplier. Times that is going to get that term. If I don't put anything there, I lose this whole term. Good. Last one in this example is e, which is 5x to the power of 5 times y cubed plus 7w5z squared. All right, let's take a look at all the pieces of this. Any greatest common factor? Not in the numerical part, not in any of the variable part. Okay, so this thing is not factorable. Not factorable. Good. Quick review. When you get a binomial or a trinomial or whatever it is, if you have more than one term, you look for the greatest common factor. You look among the numerical part of the term and then among the variable part of the term. You pull out those factors and then you see which factors are remaining from each term. If you come out with that there's nothing remaining, it's been taken care of, 3 divided by 3, you have to remember that still results in a factor of 1. Okay? Okay, example 3 helps us break out a step and we're looking at a binomial common factor. So for 3a, you have this expression, 3x times y plus 1 plus 7z times y plus 1. So when you're looking at this, it looks like a bunch of terms, but these two terms, y and 1, they're grouped. So we're going to consider that group as one term. Sorry, as one factor, as part of this term. Same thing here, y plus 1. That's a binomial. There's two terms in that group, but we're just going to consider it one group together. It's being multiplied by this, so that makes this one term. So now what we really have is just a polynomial with two terms. One term here, one term here. And there's something common to each of those terms. What is common to each of those terms? The y plus 1. It's a factor inside both of these terms. So I can actually divide this term by y plus 1, and I can divide this term by y plus 1. That makes it the greatest common factor. Now, if I pull out that greatest common factor, what does it leave me with? Well, in the first term, it leaves us with 3x. And the next term, it leaves us with positive 7z. So we pulled out a greatest common factor. That greatest common factor happened to be a binomial. This is just a part of what you're going to run into when you start factoring slightly more complicated trinomials and polynomials. Okay? Let's look at b. b is 2x times x minus 3 minus 5 times x minus 3. Well, we can factor out, again, we consider this as one term, where it has x minus 3 as a single entity within that term. And here we have x minus 3 as a single entity within that term. So our greatest common factor between the two terms is x minus 3. Let's pull that out. That's going to leave us with 2x here. And it's going to leave us with a factor of negative 5 there. So the result then is the product of two binomials. Okay? This and this have the exact same value. We haven't changed the value. 2x is still being x minus 3 is still being multiplied by 2x, and it's still being multiplied by negative 5. We have not changed the value at all. We've simply expressed it as the product of two binomials, which again is just a helpful tool. It's called factoring. It gives us a lot of information about the polynomial. Good. Carrying on. Example 4, factor by grouping. Now we're going to take what we learned from example 3 and we're going to put it into practice. So a is ax plus ay plus 2x plus 2y. Now there's actually a couple of different ways to do this. You could say, if I'm going to group two terms together, I could group these two terms together, and they have a common factor of a, and then I could group these two terms together. They have a common factor of 2. So let's do it that way. In these two terms, I can rewrite this part. I can factor out the common factor a, leaving me with a binomial that still has a times x is ax, and a times y is ay. And then I move over to the next term. I'm going to put that plus sign there. And now I'm going to factor out the common factor here. That's easy to see. It's 2. That's going to leave me with x plus y. Well, now we're in an example 3 situation. We still have two terms, and we have a binomial common factor. So I'm going to pull out that binomial common factor. I need to make sure that it gets multiplied by a, and that it gets multiplied by positive 2. Done. Okay? This is called factoring by grouping. We didn't look at the whole polynomial altogether. Instead, we grouped the first two terms, and we grouped the second two terms. Okay? The other way to do this one, and I'm not going to do it, but we could actually rearrange. Because it's a string of polynomials connected by addition. Addition is commutative. That means I can do it in whatever order I want. I could have written this polynomial as ax plus 2x plus ay plus 2y. In which case, I could have grouped these two and these two. Here I could have factored out the x. And here I could have factored out the y. Now my common binomial is a plus 2. and I need to make sure that that's multiplied by x, and it's multiplied by y. We're going to do the next one together, so don't clean up yet. There's one more. Example B, 9x squared plus 15x plus 3x plus 5. Now in this example, there's a whole bunch of x's, except that last term doesn't have an x, so I can't factor out x from all of them. There's a whole bunch of multiples of 3, a couple multiples of 3, and a multiples of 5. But I can't pull out the same thing from all of them. So that's a situation where I'm going to be factoring by grouping. Now, I can do this two different ways. Again, I can arrange it so that the 15x and the 5 are together, because then I can easily factor out a 5. And that from the 9 and 3 I could factor out, or I could just leave them as they are. Okay? And start factoring by grouping. Group the first two. They each have a factor, the numerical factor of 3, and they both contain at least one factor of x. In 9x squared, if I divide out 3x, I'm left with 3 and a factor of x. And if I divide 15x by 3x, I'm left with 5. If I look over at my next two terms, I don't see anything in common, but this is a situation where what can I factor out of this group? What's a factor of everything? 1. I can factor out a 1. That leaves me with 3x plus 5. And now I'm in the same situation where I have two terms. They have a common factor. It's a binomial factor, 3x plus 5. I need to make sure that that 3x plus 5 gets multiplied by 3x, and that it gets multiplied by 1. And now I have the exact same information in each row. It's just written differently. If you don't like doing it that way, you could rearrange it. You might say, oh, well, 9x squared should be right beside 3x, and 15x should be right beside 5 in order to help me do this. Now I can see that 3x is factorable from this group, leaving me with 3x plus 1. And from this group, I can factor out a 5, leaving me with 3x plus 1. And look what ends up happening. You have the exact same two binomial terms in your factorization. 3x plus 1 needs to get multiplied by 3x and needs to get multiplied by 5. Okay? Factoring, super helpful. There's all the steps you need to know, and enjoy your practice problems.